Let's move on to question 5. As you can see, this is a geometry problem. It reads as follows. Consider 3 circles. Okay, you can have a look at the picture while this goes on. With centers P, Q, and R. As you can see, P, Q, and R, such that each pair of circles is externally tangent. So every pair, these two are tangent to each other, those two and those two, right? Now suppose we have another circle, center O, on the line segment QR. So O is on the segment which joins the two centers of these circles, such that each of the 3 circles is internally tangent to it. Well, you can see, you got a large circle, and each of these circles is tangent to the large circle. And we require to show that angle QPR, this angle here, is acute. All right. Well, it's kind of a question that you really don't know where to start. To show that an angle is acute, you could do 2 things. You see, this long line here is a diameter. So it's possible you could take this contact point, join this, and join this end to that point. This angle so formed is a right angle, and you somehow try to show that this angle here is smaller than that one. So that is one of the ways of doing it. And I must say that I tried at length to prove it like that, and I couldn't do it. Anyway, let's see how I did it. So what we did was, let's give names to the radii of the circle. Let's call this radius A, this radius B. So you have that this is A, and this is B. Now there is another circle here which is tangent to this one. That's got its own radius. I'm going to call it X because I want to actually try to calculate X given A and B. It's an interesting problem. Is it possible to draw the circle which is tangential to, given the 3 circles, this one, and the large one, how do you draw the circle? But to do that, one of the things you need to do is to know what the radius of that circle is. Now, so I'm going to call it X. What else do we have? We have that this O is the center of the large circle. Now, we know what the diameter of the large circle is because it's 2A plus 2B. 2A plus 2B. They're touching each other. So these centers, when circles touch each other, their centers, the line that joins the centers is always goes through the point of contact. As you can see, this goes through the point of contact. It's not very difficult to prove because there's a common tangent here, a tangent to both circles at the point of contact, and that whole angle is 90 plus 90, so it's a straight line. Anyway, so the diameter of the large circle is 2A plus 2B, and therefore its radius must be a plus b. So, but the radius is the distance from here to here. So this has to be b. Radius is a plus b. And this distance here from here to here has to be a. All right, so you got those situations. I'm going to try to, you see, I'm looking at this triangle here because this angle theta, I want to show it is acute. Now the next thing is that in this triangle here, I have three sides, A, B, but in terms of A, B, and X. And therefore, you can use the cosine formula to get an equation for this triangle using cos theta. And if you want to show that theta is acute, then all we have to do is to show that cos theta is positive, right? Because if theta is acute, cos theta is positive. But the moment theta becomes obtuse, then cos theta is negative, because cos is negative in the second quadrant. All right, so this is the background. Let's go ahead and try to use the cosine formula to calculate cos theta. Okay, I've got this diagram, the same diagram. You will see the only thing I don't have in this diagram is the fact that this part here, from here to here, is B. The reason is OA is the radius of the large circle, but the radius is A plus B, because the diameter is 2A plus 2B. So this part is A, so this has to be B. The same thing, from here to here is A. Right now, I don't really need that. I want to go to, well, what we do know is QR is equal to A plus B. That's the important thing. So cosine formula. So what does it say? I'm going to apply the full cosine formula to this triangle here, PQR. Okay, I've got cos theta. Let's look at the side opposite cos theta. A plus B all squared. That's the side here. Is equal to that side, which is A plus X all squared. This one is B plus X all squared. Minus 2 into A plus X into B plus X becomes cosine of theta. Minus 2, the product of these two, cos theta. So you can say that cos theta can make it the subject of the formula. If you bring this whole thing to this side, and I'll have 2 times this cos theta. So the denominator is 2 into A plus X into B plus X. I'm missing out a step. I bring this this thing to the left-hand side and dividing by the coefficient. So what do you have here? You have A plus X all squared plus B plus X all squared minus A plus B all squared. You bring this to this side and that side. Okay. Now, the denominator is positive because all these A, B, and X all radii of circles. So the denominator is positive. And so we want the numerator to be positive. To prove cos theta is positive, and that will be, then theta will be acute. That's what we really need to show. We need to show that theta is acute. And I'm saying rather than do that, show that cos theta is positive. So that's the goal. So what do you have? You have the numerator to show. Sorry. So in other words, we need to show that the numerator is positive. The denominator is already positive. To show that 0 is less than, okay, let's take the numerator. We have a squared plus 2ax plus x squared plus b squared plus 2bx plus x squared. Then you got a minus sign here. So it's minus a squared minus 2ab minus b squared. All right, so you got a squared minus a squared cancels, b squared minus b squared cancels, and you are left with to show that, what are you left with? You got 2x squared minus, to show that's 2x squared, I got x squared plus 2ax plus 2bx minus 2ab. I'm going to show that that is positive. I must show this, right? Which is the same as if you divide by 2. That is, I want to show that x squared plus a plus b times x minus ab is greater than 0. All right. Now, to do that, I need to calculate x. The problem is that I got a negative sign here. See, the numerator is positive, denominator is positive, so I need to show that the numerator is positive. This is what I need to show. But there's a minus sign here, and I got no idea as to whether this whole thing is positive, and I don't even know what this x is. So I need to calculate the x and try to see whether I can show that this is positive. All right. So now that's the next thing that we have to do. I'm going to delete all this and just let me delete all this. So I want to show that x squared plus a plus b x minus ab is greater than 0. That's the goal. Now, I got the same diagram here, except that I've taken this OP and I've extended it to meet the circumference. And this part is also x, because this is the radius here. And OP, you see, we know that these 3 radii are equal, so that should be able to help. But I need to have OP. Let me give a name to OP. Let OP be equal to P, small p. So what do I have here now? I have that this is B here, and this is A, and then this is P from here to here. And here I've got A plus X, I've got B plus X. I got all these sides here in this triangle in terms of A, X, B, and P. There are four unknowns, unfortunately. Well, A and B will be given. So there are two unknowns here, P and X. Right? So how do we calculate that? Now, to calculate this, we actually use a interesting result, which is a little known, but I suppose by the time you get to the third round, you should know a little bit more than school geometry. And this result says the following. If you got any triangle and a Servian is a line which joins one vertex to a point on the other side. So you got all these lines. There's a very nice equation that links up these five lengths. Right? You can use a cosine formula too, because you got these three lengths, you got these three lengths, and you got these two angles. The cosine of this is equal to the negative of cosine of the other one because these two angles supplementary. Use a cosine formula and you can eventually come to this interesting result, which was actually first stated by Stewart. It's not a very complicated result, but at least he's given his name to this, which I think people must have known a long time ago. Anyway, what it says is, we call this A and B and C. This side of this triangle, which is m plus n, A squared, no, the way it works is, yeah, m, this times q squared, that piece times the other opposite one, plus n times p squared, similar kind of thing here, is equal to d squared into a plus mn, where a is equal to m plus n. I'm calling it small a because it's the side opposite angle A. Normally you give. This is d squared. So this is Stewart's theorem. This times q squared plus that times p squared is equal to this squared times that plus mn. It's a sort of tricky formula because you got so many numbers here, M, N, Q, P, A, and D. There's 6 symbols here. All right. And so this is so that's the statement of Stewart's theorem, which I've got here. And I refer you to my book called 1000 Mathematics Olympiad Problems. And in that book, I prove this result. But just for the sake of completion, I can prove it because it's quite simple to prove. Let's call this theta. Call this 180 minus theta. So you have, if you apply the cosine formula to the left-hand triangle, you got c squared is equal to m squared plus d squared, m squared plus d squared, minus 2md times cos of 180 minus theta. But cos of 180 minus theta is minus cos theta. So I'm going to change the sign there, put theta there. And then likewise, in the other triangle, you got b squared here is equal to n squared plus d squared minus 2nd cos theta. That's a sort of sine formula, cosine formula. I can eliminate this term here by multiplying this by n and multiplying this by m and add. So I multiply this by n. I want mnd, mc squared plus multiply this by m, yeah, plus mb squared is equal to, now I'm multiplying this by n, so I have m squared n plus nd squared, right? And then I'm multiplying this by m and I'm adding it, plus mn squared plus md squared, right? And this is the same as the left-hand side. I've got mb squared plus nc squared equals, now on the right-hand side I've got, I can take out mn as a common factor. Mn as a common factor here. I get m plus n, which is a. M plus n is a. And I also have, if I take this out, I got d squared as a common factor. And once again, I got the other factor is m plus n, d squared, nd squared. So I got a here. And that is how you get a into d squared plus mn. I think that's what I wrote. I'm not sure whether I wrote that originally or something else. Anyway, it is this into d squared plus mn. Right. Now, why do I need all this? Because in my diagram here, I have that scenario in the PQR triangle. I got these 5 links given. So let me now try to apply the Stewart's theorem to that. Okay, I've relegated all this inside here. I don't know whether this maybe this diagram is too. Should try to make this a little bit bigger. I can't seem to make it bigger, unfortunately. It normally should be able to, but I can't seem to make it bigger. Anyway, hopefully you can read this thing. We are going to focus our attention on this triangle. This triangle here. I got that side, and here I've got B, and here I've got A, and I've given a name to this length here. I called it P. Right? PO is P. Okay, and also you have that R, which is large radius. that is equal to P plus X. It's from center to C, it's P plus X. And it's also equal to A plus B, we saw. So we'll just preserve all those symbols. Those few things which we already know. And now let's apply Stewart's theorem. Stewart's theorem says B into that squared, B plus X all squared, plus A into A plus X all squared, A into A plus X all squared. That's equal to this whole length here, A plus B, into, we said it's that length there, P squared, plus the product of these two, AB. Okay. Now, I'm going to eliminate X from this thing. X is equal to A plus B minus P from here. P plus X is a radius, and that's the same as A plus B. So I can't find X in terms of P. So I got a P here, but I'm going to reduce this, take out one of the unknowns. That should be able to help. So then if X is this, what is B plus X? So you have B into, now B plus X is A plus 2B minus P. If you're adding B to X, then A plus 2B minus P is all squared, plus A into A plus X is 2A plus B. Minus P all squared. I'm just simplified that, substituted that, and here there's nothing to substitute. You got A plus B into P squared plus AB. Now it's getting very hairy here because I got a square term here. So this is B. Now this, I'm going to say this minus this. So it's expand this thing as a square term. I'll have A plus 2B all squared minus 2P into A plus 2B minus 2P into A plus 2B plus P squared. That is just this term here. Now, this other term is similar, plus A into, now I'm going to square this thing here, but regarding this as a single term, 2A plus B. So you get 2A plus B all squared minus 2P into 2A plus B. That's a middle term, minus 2 times this plus P squared. Is equal to A plus B to P squared plus AB. All right, I don't think you have ever seen anything as long as this. I mean, even this needs to be expanded. All right, I'm going to multiply this whole thing by B. I'm going to expand this thing and multiply by B at the same time. So I get A squared B. When I expand this, the middle term is 4AB times B. So it's 4AB squared. The last term is 4B squared times B, which is 4B cubed. That's the thing about mathematics. You have to keep going and going and going, and you might give up. You say, "Oh, I'm on the wrong track." But you will see just now how beautifully everything just melts out. I was very surprised when I came to this result. I haven't seen this thing before. Uh, Now I finished with that one. So I'm still multiplied by b. So I got 2pb. So minus 2abp, 2b times 2pa. Yeah, I got minus 2p minus 4bp. I'm multiplying by b, so it's minus 4b squared p. And then I got b times p squared. Right? And that is equal, well, I am still, yeah, I got the b term outside. I must still do this. Let me put this underneath here. So now a times 4a squared, which is 4a cubed. The middle term is 4ab. I'm multiplying it by a. The last term is b squared, and I'm multiplying it by a. Yeah. And then I'm still multiplying everything by a. So I got a times 2p is minus 2pa times 2a minus 4pa squared minus 2pa times b gives you minus 4pab. And then you have a times p squared, which is ap squared, equal to a plus b into p squared plus ab. Right, now let's see, what have we got here? Let's take the cube terms out first. You got 4a cubed plus 4b cubed. I'll take those things out. Then let me take the a squared b terms out. A squared b plus 4a squared b is 5a squared b. Then I go to the ab squared term. 4ab squared plus ab squared gives you 5ab squared. Minus 2abp I think it's supposed to be 2 here. 2p times b is 2pb times a. Right, so there's supposed to be 2. So you get minus 4abp. So that takes care of those two. What else? What are the survivors here? Then you've got oh yes, you've got minus 4p. I can put minus 4p into a squared plus b squared. Take out minus 4p as a common factor. And here you got p squared is a common factor here into a plus b. And on the right hand side, you got a plus b into p squared plus ab. Ooh! I don't think I've ever done anything so complicated. All right, now I'm going to create some space. I'm really interested in this last equation. But one of the things that happens is this thing simplifies. Okay, now what happens here is that a cubed plus b cubed, a plus b comes out as a common factor. I claim that a plus b comes out as a common factor right throughout here on the left-hand side. That a plus b is a factor of the left-hand side. Well, not quite. Let me just, let's not jump the gun. Every time I tried this, I made a lot of mistakes because I want to do a lot of things mentally and get myself messed up. Okay, I'm looking at the last line. I'm going to put 4 into a cubed plus b cubed. Right? That goes there. Here, I've got 5ab into a plus b. ab comes out of common factor. And then I got a plus bp squared. I'm going to take the negatives and put it on the other side. A plus b p squared. Right? Now these negatives, I'm going to put it to the other side. This is equal to a plus b into p squared plus ab. That was on the other side. But now I'm going to add these two other things, these two negatives. So I'll have plus 4 abp put that on the other side. And here I got 4p into a squared plus b squared. Well, let's put this on that side. So I got an a plus b as a common factor, and I got an equal sign here, like that. Now, a plus b comes out as a common factor here. Now remember, we said that p plus x is the same as a plus b. Oh yeah, okay. Now, this is 4 into a plus b, a squared minus ab plus b squared, plus 5ab into a plus b. Now, there's a plus b times p squared, and you got a plus b times p squared here. There's a minus sign in front of this. So that cancels. And what you're left on this side is minus a squared b. Oh, p squared minus ab into a plus b. Right? It's p squared into a plus b. That goes up there. And you have what's left here is minus ab into a plus b on this side. And on this side, yeah, we got 4abp plus 4p into a squared plus b squared. See, I took all the p's and put them on the right-hand side. I want to make P the subject of the formula, you see. That's why I've shoved everything to the side. Now let's just take out all this stuff here. I could have asked you to do this as an exercise, but you probably would have thought it's leading nowhere. So I couldn't resist the temptation of doing it. You see, I got 5ab into a plus b minus ab into a plus b. So that gives you 4ab into a plus b. Now why? Now you see that the 4's are common right throughout here. See? So a plus b comes out as a common factor. I can cancel the 4's. Right? What am I left with? Now I got a plus b as a common factor here. And here you got a squared minus ab, the 4 goes off, plus ab plus b squared. A squared minus ab plus b squared plus ab. So all this goes off now. Right? And on this side, what have I got? I've got abp p comes out as a common factor. So you can take p into a squared plus b squared plus ab. And there we have it. We have that p is actually equal to a plus b into a squared plus b squared all over a squared plus b, a squared plus ab plus b squared. Now that is p. And we still have to find x. But remember that x, p plus x is a plus b. Where p plus x is the radius of the circle, of the large circle, and so is this. So I can find x. X is equal to a plus b minus all this stuff. Minus a plus b into a squared plus b squared all over a squared plus ab. When a plus b comes out as a common factor, so the radius of the circle here is actually if you take it as a common factor, then what are you left with? I'm going to take out all these things here now. So even if you didn't follow it, I've got the whole solution typewritten, so you can look at it there. I'm taking out a plus b as a common factor. What's the other factor? The other factor is 1 minus, taking out a plus b, a squared plus b squared all over a squared plus ab plus b squared. And that is when you put the common denominator a squared plus ab plus b squared, and you're subtracting that, you just have ab. So the other term here is ab over this. So x is actually equal to an important formula, so I'm not going to hide it at the bottom here somewhere. X is equal to, we said is A plus B times what remains, and that's what we calculated here. And that is A plus B times this, which is AB over A squared plus AB plus B squared. So that is the radius of the circle. We're not over yet. We just found X in terms of A and B. Now remember, we needed to calculate X squared minus A plus B so you can work out X squared minus A plus B times X. This was what we needed to calculate, or plus minus AB. And I wasn't sure whether that is positive. Now, if you work this thing out, I'm not going to do it. I think now you can do it. Square this thing here and subtract this thing here. You'll see you'll get a term which is only positive. Is an expression with only positive terms. So, and this is your cosine theta. So cosine theta is positive and theta is acute. You would think that to prove a simple thing like theta is less than 90 degrees is such a trivial thing. Maybe there is some easier solution to this, but the solution that was given on the website is actually wrong. There is a solution, and that's a much shorter solution. So I had to correct it and made my own formula here. This formula I'm very proud of. I think, I don't know whether it's known. I'm going to try to see whether I can get it published. If it hasn't, it's not known. Okay, so here we go. This is question 5. And we now come to the very last question. But before that, let me just show you what the answers were. I missed out a lot of calculations here, I think. Maybe I did. Okay, this is the first part where I needed to get cosine theta. And I call P equal to OP, as you can see. And then, so this is where we made all these terrible calculations. And I got P, you can see P is the same as what I calculated. There it is here, P is equal to this. And then that's not the end of the story. We needed to calculate X. So there's X, yeah. And you will see I got X to be another rather complicated, but it may look complicated, but it's very beautiful because there's a symmetry in it. See? So there's X. And you can see it's got only A and B. There's no negative signs. So this is positive. So this is your cos theta. Positive. All right. So now I've exposed all these. So you can go and check the thing out. It'd be nice if you can redo the whole thing on your own and see whether you can do all the algebra. Very, very excellent exercise in algebraic manipulation. I made a lot of mistakes while I was doing these calculations. All right, now we go to the last question. There are 6 questions. Let n be the set of positive integers. In other words, 1, 2, 3, 4, and so on. And let f be a function. Oh, this is another one which is similar to the previous one. We had the we had to find an f there, and we said it's a cubic polynomial. So here again, you call these functional equations. I don't know why they gave two functional equation questions in the same paper. It's not good. It's not very nice. All right, now you've got the f satisfies this formula. F of mn equals m times fn is n times fn. For all positive integers m and n, they have to be positive integers because f works only on positive integers. But here, this n subscript 0 means it's positive together with 0. So it is possible that your target, could be 0, but the rest of them are all positive integers. And now, obviously, this question was set in F 2024, and they say F of 2024 is 10,120. Now, prove that there are two positive integers m and n, with m different from n, such that m equals f of n. In other words, when you plug in m into your function, we don't know what the function is. We only got the function satisfies some kind of a rule here. We are not given the function, but you have to, maybe we have to find the function and then show that you have two distinct inputs. I call these inputs such that the outputs are the same. And you're given only one piece of information, namely f at one very, very specific value. You don't know any of the other values. So it looks like quite a hard problem. Okay. Most of the time, I must admit that I have to look at the published solutions to give myself some lead, but my solutions are not identical by any means with the published solutions. Sometimes it's completely different. This one, I can't remember exactly what the position was. Okay, now let's have a look at this problem. And so what are we given? We are given that f of mn is equal to m f of n plus n f of m. All right, for all values, and it's f is from n to n0. The m and n are natural numbers. Okay, that's quite important. Now, can we do anything with this? Well, let's try m and n both equal. M equals n. Then you have f of m squared, m f of m, and m f of m. So they both are 2m f of m. Okay. Oh, which now tells you that when m equals 1, so I'm going to put this in brackets. In particular, this is a general formula here. If m equals 1, you have m equals 1. Twice f1 is equal to f of 1. So it means f of 1 is 0. Okay, so we have one other value, f of 1. But observe, we don't want to find f. We just want to find out whether there are two different numbers which have the same output. So we've got f of 1 is 0. So if there is if for some positive value, we have that f of n equals 0, we are done. And what does that mean? It means now that we have two different values which have got the same outputs. F of 1 equals f of n, but n is not equal to. Oh, for some n greater than 1. And because the inputs are all natural numbers. So if there's some n greater than 1, then you got f of n equals f of 1, and n is not equal to 1. Right? So let us assume that f of n is not equal to 0 now. It's greater than 0 for all n greater than 1. Right? Whenever n is greater than 1, we don't want f1. If f1 is 0, then we are done. So we can make this assumption. Bear that in mind, is quite useful. Okay, now the thing is, I got a f of m squared equals 2m f of m. Let's try m cubed, f of m cubed. And remember, this formula here is when you got a number which is a product of two things, you can split it like this, right? So this is f m times m squared. So this is equal to m squared times f of m plus m times f of m squared, right? This times f of m plus that times. Now, f of m squared we just saw was 2m f of m. So you got m squared f of m squared was 2m f of m. So you get m squared f of m plus 2m squared f of m. So that gives you 3m squared f of m. Now you see, now you got f of m cubed is 3m squared f of m. F of m squared is 2m. So we suspect the conjecture actually I don't need this. So let me not. But you can try to prove it if you wish. I'll just put this down as a fact. I wouldn't put it as a conjecture. We don't really need it. That is why I'm not going to bother about it. But fact, f of m to the power of k is always equal to k times m to the k minus 1 times f of m. And I'll leave this to you to prove it. Okay. Now, so where do we go from here? Let's have a look at just what is given. I just want to look at 2024. Okay. Now, also, you can extend this thing. F of ABC is equal to AB times f of C plus C times f of AB And that is equal to AB times f of C. F of AB is A f of B plus B f of A. And when you simplify this, you get AB times f of C plus BC times f of A plus CA times f of B. See? ABC, BCA, CAB. There's it. CA times f of B and BC times f of A. So you get a nice, you can extend this formula that is given to the product of three numbers. So that's quite useful. And the rule is quite simple. You just take two at a time, and it's f of the other one, and you add all of them up. Okay. All right. So let's. We probably will need all that. So where do I go from here now? Let's see what is given. We're given that the 10,120 is equal to f of 2024. Now, the sharp reader or the sharp student will realize that this number here is only 5 times this. So it's just not a random number. 5 times this is this. But we don't use it straight away. But it will come up indirectly. Now, let's try to factorize this because we know some things about factorization. So you got, this is f of 2024. Let's put this down here. 2024. You can take out 8 as a common factor. And you get 253. 253 is 11 times 23. So this is the same as, I can write this as a product of three numbers. So 8 times 11 times 23. Okay, and now we can use these things here. So you got, this is the same as 11 times 23 times f of 8 plus 8 times 23 times f of 11 plus 8 times 11 times f of 23. Let's take them one at a time. 8, f of 8, the others are outside. 11, f of 11, the others are outside. Just this is what we got here. Now the interesting thing of this is that 11 goes, this one here, when you factorize this number here, as I said, it's 5 times this. So this is equal to, when you factorize this, I just want to clear up the space here. And I want to put this in this line. It's one of the reasons why I cleared the space. So I want to put plus 8 times 11 times f of 23. And I'm going to put this 10,120 on the right-hand side. This is 5 times this. So it's 5 times 8 times 11 times 24. Because this is 5 times this, and that is 8 times 11 times 24. Now watch. You see, 11 goes exactly into this. It goes exactly into this. And it goes exactly into this. Therefore, 11 is a factor of 8 times 23 times f of 11. See, the reason is this is 11x, this is 11y, and this is 11z. So when you bring all to the other side, you have 11 times z minus x minus y, whatever it is, but it's 11 times something. So therefore, 11, this number here is 11 times something. So 11 is a factor of this number here. But watch that 8 times 23 and 11 got no common factors. So if 11 is a factor of this, 11 will have to be a factor of f of 11. Because these two have got no common factors. So when you factorize this thing completely, the 11 will be absorbed into that one. This makes no contribution to the 11. Right? And you have similarly, (23) is a factor of f of 23. Good. Oh, this is 23 here. This is 23 goes into this, 23 goes into this, 23 goes into this, therefore 23 goes into this, and 8 and 11 has got no common factors with 23, so 23 is a factor of that. And then also 8 is a factor of f of 8 for the same reasons. Now this 8 is 2 cubed. See, earlier on we said f of m cubed is 3m squared f of m. Right? If you recall, we've actually proved this. So this is 2 cubed, which is f of 8, is 3 times 2 squared, it's 12 times f of 2. Right? If you put m equal to 2, you'll get this. So this part here is 12 times f of 2. So 8 is a factor of 12 times f of 2. So if you divide on both sides by, so 2 is a factor of f of 2 also. Okay? Now, where is all this getting us? We're just analyzing this thing here and making conclusions. Doesn't look as if we're getting too far away. But at least we're getting somewhere. We've got these kinds of things. So we can say, yeah, actually, we can make some good progress with this. Why? Because f of 11 then is equal to 11 times an integer. A positive integer. Okay, let's put it this way, sorry. F of 11, we'll just call it 11p. F of 23 is equal to 23p, 23q, and f of 2 is equal to 2r. Because all these are, and this p, q, and r are all numbers which are greater or equal to 0. P, Q, R are all greater or equal to 0 because the outputs are all the positive numbers including 0. But I can't have P equal to 0 because then f of 11 is equal to 0, and that will mean that my problem is solved. And the same thing with this. See? So we have that if any one of them is 0, then solved, right? If any is 0, we are done. So we can assume that f of 11 is greater or equal to 11. And same with f of 23 is greater or equal to 23, and f of 2 is greater or equal to 2. Right. So where does all this get us? I'm going to go back to this thing here. I'm not dropping these things out because we're going to use them. Now, on the left-hand side, I got 1, 2, 1, 2, 0. Now, this is greater or equal to, this is 11 times 23. And we said that this f of 8 is 12 f of 2. And we said f of 2 is greater or equal to 2. And here you got 8 times 23. And f of 11 is greater or equal to 11. And here you got 8 times 11 greater or equal to 23. Now, if you look at all these, you see the 23 times 11 times 4 is a common factor here. 23 times 11 times, oh, I'm sorry. This is 12 times 2, it's 24. 12, f of 2 is greater or equal to 2, so I should have 24 here. All right, now you'll see that 8 times 23 times 11 is a common factor. So this is 8 times 23 times 11 is a common factor. And 11 times 23 times 8, so there's a 3 which is out here. 8 times 23 times 11 is 1. And here too, you got 8 times 23 times 11 is 1. And this is, oh, I'm sorry, this is supposed to be 8. And this is exactly 2024 times 5, which is equal to 1,120. Right? So you got 1,120 is greater or equal to 1,120. So in other words, this thing here, this whole thing here is exactly equal to 1,120. Right? The greater or equal can be replaced by equal sign. Right? Which means that all these f of 2, these are all actually equal. If any one of them is greater, then we have a contradiction. Then you have that 1,120 is bigger than itself. So all of them are equal. So here too they are equal, and here they are equal. So now we know what exactly what f of 2 is. It's equal to 2. f of 23 equals 23, f of 11 equals 11. That's quite remarkable, because they only told you what f of 2024 is, and we were able to actually calculate three other outputs. And in those three outputs, the outputs are exactly the same as the inputs. F of 2 equals 2, f of 11 equals 11, f of 23 equals 23. But f of 2024 is not equal to 2024. It's equal to 5 times that. Okay, so now where to from here? So what we're going to do now, this is the hardest part. So we have that we know the f of 11, 23, and 2. So we can say if we have 2 to the a times 11 to the b times 23 to the power of c, right? It's equal to, now we did this before. We have 11 to the b times 23 to the c, f of 2 to the a plus. Now we'll take the middle one. This time you'll have 2 to the a times 23 to the power of c, 23 to the power of c times f of 11 to the b. And then finally, you got 2 to the a times 11 to the b times f of 23 to the power of c. Now we know that this is equal to 11 to the b, sorry. Now I'm going to use that formula. Oh gosh, I asked you to prove it as an exercise. I thought I didn't need it, but I do need it. So this is actually equal to 11 to the b, 23 to the power of c. And this is like the derivative formula. So if you know the derivative formula, so this is a times 2 to the power of a minus 1, right, times f of 2, which is 2. We know that f of 2 is equal to 2. Here you got 2 to the a times 23 to the power of c times 11, f of 11 to the power of b is b times 11 to the power of b minus 1 times f of 11, which is 11. Sorry, this is just going down here. I'm going to repeat this thing here. It's 2 to the a times 11 to the b times f of 23 to the power of c. I'm repeating that because I want to rub it out. It's right in the way. All my mathematics is suffering the weight of gravity. Okay, I've got this one here. The second one was, so 11 to the power of b, 23 to the power of c. And here I have a times o. Oh, I'm looking at the second term now. Sorry. I finished the first term. I'm looking at the second term now. So the second term is this. This is 2 to the a times 23 to the power of c. And here you have b times 11 to the b minus 1 times f of 11, which is 11. Here you have 2 to the a, 11 to the b, and here you have c times 23 to the power of c minus 1. I'm looking at this one here now. and times f of 23, which is 23. Right. Now, as you can see, this a lot of calculations here. Now, the nice thing about this is that, let's put it this way, 2 to the a times 11 to the b times 23 to the power of c is a common factor right throughout here, right? Here it is 11 to the b, 23 to the power of c, and these two when multiplied gives you 2 to the a. And the remaining factor is a. Right. Now, again, you take 2 to the a, 11 to the b, 2 to the a, 23 to the power of c, and these two, when you multiply it, you get 11 to the b. So that comes out as the common factor. You got b, and likewise, this is c. So now you've got a general formula for anything which looks like this. See? And now, at this point onwards, I find it very difficult to justify this. You see, you got f of n is equal to a plus b plus c times n. Right? Where this is, and it's exactly the same thing. So f of x is equal to a plus b plus c times x, but it's just for these numbers of this type. All right, now comes the insight. You try to find a, b, and c such that you got two different values of the inputs give you the same output. Okay, and I don't know how these people arrived at this thing here. I can not justify it. I'm just looking at the solution. I couldn't do it. So you can say, let a equal to b and c equal to a plus 1. Then what do you have? You have 2 to the a is equal to b. So you'll have 22 to the a is equal to b, times 23 to the a plus 1. Right? Because the c is a plus 1. And here you have a plus b plus c, which is I think c is b plus 1. So a is equal to b. So these two are the same. You see, at this stage here, for a particular choice of these become consecutive numbers. You can make them 23. Okay, let a equal to b. Let's just stop there, see what happens. Let a equal to b. So then what you have here is f of 22 to the a times 23 to the power of c is equal to 2b plus c, right? And then now you let c be equal to a plus 1. C equal to a plus 1. Then you'll have f of 22 to the power of a, 23 to the power of a plus 1 equals 2b plus a plus 1. Right. So that's one situation. And in the other situation, you let b equal to c. And then what do you have? Then you have that f of b is equal to c. So you have 2 to the a no, you don't want b equal to c. You want still a equal to b. Ah, you let b, yeah, you do this. Sorry, this is a very tricky here at this stage. I'm going to do this here. I'm going to put f of 2 to the a plus 1, 11 to the b plus 1, make it a plus 1, and 23 to the power of c is equal to it's make it b plus 1 and b plus 1. So you have a plus 1, a plus 2b plus 2. A plus 1, and b. So here you have 2b plus a plus 2. Something like that. And you'll see the answer later on. And then what you do is you let this one here be 22. And then in that case, this one here becomes 23. It's something like this. Let me just see what the actual answer is. I'm going to cheat. But this is a very unusual way of doing things. Okay, so this is where I am. This is where I was, right at the bottom. F of 2 to the a times 11 to the b times 23 to the c is equal to this. Let's have another page. And this is what I've done here. Finish it off. I said in particular, right, now I give specific values to a and b, and I get some answer. And the second one, and this is what I was trying to get to. I was nearly there. So when you use particular values for a and b, and you let c be equal to b plus 1 in one case, and c be equal to b in the other case, then you get this kind of a thing. And now if you let x be equal to this and y equals that, you will see, let me point to this. Yeah. So f of this is equal to that, f of that. They look rather complicated. But if you let x be equal to 22 to the power of a times 23 to the b plus 1. Now this is 22 to the power of a. This is 23 to the b plus 1. Then you get, this is the whole thing here is x. So you got f of x is equal to, and then you get this, and y, if you let y be equal to 22 to the a plus 1 times 22b, you have that, and you will see that these two are exactly the same. Huh? You will see that f of x equal to f of y, right? Whenever this happens. But x need not be equal to y, right? Because you have this equation that 2a plus b is equal to 21. And you can choose a and b in such a way that you have that x and y are different, but f of x equal to fy. That is the whole idea, to show that there are two different values of the inputs which give you the same output. Look, I'm sorry I messed up with this thing here, but I found this problem to be extremely difficult, and I don't think I'll be very, very surprised if even one student in the whole country got it right. All right. So, but it can be done. All right. So that brings us to an end of this paper. It's been a long session. Thank you very much for listening.